This is the fourth lecture of our lecture series in geometric optics. So far, we have seen in lecture 1 where we talked about the ray model. In lecture 2, we talked about the refraction of light. And in lecture 3, we talked about lenses. Now, in lecture 4, we talk about reflection of light. Our previous lecture was about lenses, but still falling under refraction. Now, in this lecture 4, our main objective, or objective number 1, is as follows. You are expected to explain what is meant by total internal reflection. I'm going to abbreviate that. Total internal reflection. You are also expected to use Snell's law. As light travels from a medium of higher density to a medium of lower density. Right. In terms of optical density. Right. In other words, light moves from a medium of higher refractive index to a medium of lower refractive index. Right. So this is our objectives. We are going to use Snell's law in this situation. We are going to analyze what happens to this light as it moves from higher density to lower density. Right. Now, let's represent the scenario diagrammatically. And we say, let's suppose this is our normal. And I'm going to take this as medium 1. This is going to be medium 1. Now with refractive index 1. This is medium 2 of refractive index 2. So refractive index 1 is greater than refractive index 2. And you remember, in this case, under this situation, theta 1 will be smaller than theta 2. And remember, theta 1 is angle of incidence and theta 2 angle of refraction. Meaning to say, when light strikes the interface, and this is our interface, this is the interface, then on leaving the interface, it refracts away from the normal. So this is our theta 1, this is our theta 2. Right, so it refracts away from the interface. Now, check. If in this case we were to increase the angle of incidence, remember we measured from the normal to the incident ray, and this is our incident ray, this is our refracted ray, and this is incident ray. Now suppose we were to increase this angle of incidence. Let's suppose the incident ray is at this position, then we would find that the angle of refraction also increases, because it would take this position. If we call this position 1, this will be position 1. If we call this position 2, this becomes position 2. So if we keep on increasing, for example, the angle of incidence, then we keep on getting an increase in the angle of refraction. Now we can get to a point where the refracted ray lies along the interface. Let's suppose at position 3 the refracted ray lies along the interface. We say this ray is grazing the interface. It's grazing the interface. So check, we started with this angle of incidence, then we increased it to this angle of incidence, then we increased it to this angle of incidence. Now each time the angle of refraction also increases. The angle of refraction also increases until we are at a situation where the refracted ray lies along the interface. Now at this situation, position 3, where the refracted ray is along the interface, this angle of incidence, the angle of incidence, we call it theta c, implying critical angle. Now the angle of refraction, theta 2, angle of refraction, the angle of refraction becomes 90 degrees. So check, at a critical angle, the angle of refraction is 90 degrees. The refracted ray lies along the interface between the two media. In other words, the refracted ray is grazing the interface. Now, let's look at Snell's law under these circumstances. According to Snell's law, we say mu1 sine theta 1 equals mu2 sine theta 2. Now check, if we say mu1 over mu2, this will be equals to sine theta 2 over sine theta 1. That's what we have. Right. So in this case, check, we are saying when the ray is passing from higher index of refraction to a lower index of refraction, then mu1 over mu2 is greater than a unit. In other words, mu1 over mu2 is greater than 1 because mu1 is greater than mu2. Right. Similarly, sine theta 2 over sine theta 1 is greater than 1. Why? Because sine theta 2 is greater than sine theta 1. Right. So, which implies that the ray, the refracted ray bends away from the normal. It bends away from the normal. Now, this is what we are seeing. Now, from analysis, it means there must be a value of theta. There must be a value of theta less than 90 degrees. In other words, theta 1, let's talk of theta 1. There must be a value of theta 1 less than 90 degrees for which theta 2 is equals to, let's say sine theta 2 is equals to 1. Right, which implies theta 2 will be 90 degrees. This is according to analysis of Snell's law. So this angle at this situation, this angle, we call it critical angle. That is, at this situation, theta 1 is equals to theta c, which is critical angle. Right. So theta c mathematically can be given by, it follows that theta c will be equals to the sine whose angle is mu2 over mu1. Right, where, as we have discussed, mu2 is the refractive index, which is of less dense medium, and the mu1 the refractive index of the denser medium. So this is how we calculate the critical angle. Now, let's make a brief analysis again of what we have just talked about. Now, we are saying, point number 1, if theta I, which is angle of incidence, is less than the critical angle, we must know that the ray incident on the interface always splits up, implying part is transmitted and the part is reflected. Right. So this statement tells us that as long as the angle of incidence is less than the critical angle, the light ray incident at the interface will partly divide, part of it is reflected, part of it is transmitted. Now remember, this coincides with the ray model. According to the ray model, when light encounters a non-homogeneous interface, part of it is transmitted and part of it is reflected. Even part could be absorbed. Right. Now, the second point is that if the ray is precisely at critical angle, in other words, if theta I, the angle of incidence, is equal to the critical angle, we are saying the incident ray precisely forms the angle of precisely forms the critical angle. Precisely forms the critical angle. It follows that the refracted ray is tangent to the boundary, at point of incidence, Right. In other words, the refracted ray grazes the interface. Okay. Now, sometimes we refer to that as grazing refraction. Now, the third point is that if the angle of incidence is greater than the critical angle, then the entire ray reflects from the boundary. Implying none passes through. Now check. What are we saying? We are saying, in the first case here, as long as the angle of incidence is less than the critical angle, the ray divides when it reaches the interface. Part of the ray is transmitted, that is refracted, part is reflected. Now, at critical angle, that is when the angle of incidence coincides with the critical angle, the refracted ray lies along the interface. But still we have another part which is reflected within the medium of incidence. In other words, the first medium. So the ray is still divided into two, again at a critical angle. But if we keep on increasing the angle of incidence to be greater than the critical angle, then the entire energy is no longer divided, but all of it is reflected within the first medium. So nothing passes to the second medium. And at that stage, we are talking of total internal reflection. So in this case, TIR, in other words, total internal reflection, is said to take place. So you should be able to represent this diagrammatically. Right. So in summary, as the angle of incidence increases, the refraction angle theta 2 also increases. and approaches 90 degrees. And the fraction of the light energy transmitted decreases while the fraction of reflected energy increases. Now check. When the ray divides into two parts, part of the energy is refracted and part of the energy is reflected. So while the angle of incidence is smaller than the critical angle, most of the energy is refracted. As you increase the angle of incidence, then the angle of refraction also increases. But the amount of energy in medium 2, or the refracted energy, decreases as the angle of incidence increases. The refracted energy decreases, and more of this energy becomes part of the reflected ray. So as you keep on increasing, eventually when the angle of incidence becomes greater than the critical angle, all the energy is no longer transmitted, but is now completely reflected. This is what we mean. Right. Now, total internal reflection finds application in optical fibers. In other words, application of total internal reflection is in optical fibers. Optical fibers. Right. Now, these are tubes. You can draw the tube like this. These are just tubes that are used to trap light within them. Now, you can have light entering. When it enters, the light hits the interface. It's reflected, totally reflected. Hits another interface. It's totally reflected, and it goes on like that within the tube until it comes out the other end of the tube. Now, here always total internal reflection takes place. So we label it TIR, 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 and TIR. Right, meaning at this interface between the two media, there is always total internal reflection. So the light is totally reflected within the same medium until it comes at the other end. Right. So the light continues to bounce within this confined environment. Right. Usually these optical fibers are made of some materials where we have what we call a core at the center, and then we have another one which we call cladding. Right. Like this. Now this is the core and this is the cladding. Okay, so the refractive index of the core is greater than the refractive index of the cladding. This is what happens. So this is how it is built up. So this other one is just a protective cover. A protective cover. So light is introduced in the core, and then at the interface between the core and the cladding, total internal reflection takes place. So it moves on like that. This is higher optical density. This is of higher optical density. This is of lower optical density. So eventually the light moves on until it comes to the other end. Right. This same concept of total internal reflection is used in diamonds. In other words, another application is in diamonds. Another application is in diamonds. When people make diamond cutting, and when they cut these diamonds, they are cut in such a way that when light enters it, it is trapped inside and does not come out. And all is because of total internal reflection. So when you see or watch or observe the diamond, you will find that it sparkles. But all is because of total internal reflection taking place within the diamond as light that enters is trapped in. Right. So basically, this is about total internal reflection. Now, let's now focus at specifically reflection itself. Reflection itself. Last time we talked about refraction. Now we want to focus at a reflection. Now, under reflection, we have a key objective which we want to accomplish. Now, our objective, which we shall call objective 2, is as follows. You are expected to distinguish between mirror reflection and diffuse reflection. Mirror reflection and diffuse reflection. Right. In other words, what this tells us is that there are two types of reflections that take place. There are two types of reflections that takes place. In other words, we have two types of reflection. Types of reflection. We have one, what we call specular reflection, and we have what we call diffuse reflection. We have these two types of reflection. So according to our objective, we are supposed to distinguish between mirror reflection and diffuse reflection. This specular reflection is also what is called mirror reflection. This is what is called mirror reflection. Right. So let's see. Let's start by looking at the specular reflection. Let's look at specular reflection. Okay, in previous discussions, we said reflection of light may occur when light travels from a medium of a given refractive index into a medium with a different refractive index. In the most case, general case, a certain fraction of the light is reflected from the interface and the remainder is refracted as it passes into the the second transparent medium. This we have just discussed when we were looking at total internal reflection. Now, a mirror is an example of specular light reflection. A mirror is an example of specular light reflection. Right. Now, how is the mirror made? The mirror itself is normally a glass sheet in front of a metallic coating. In other words, here they put a metallic coating. This will be a glass sheet. A glass sheet. It will be in front of this metallic coating. Right. This is how a mirror is really made. It has two materials. Now, this metallic coating, normally we refer it as a solid material at the back here, while this one is transparent. Right. So you can see that when light comes in, it actually enters this transparent material and then gets to the solid material, and then reflection takes place. Right. So the reflection partly takes place here and another takes place here at this coating. It's just a small thin coating. It's a thin film coating, metallic coating at the back here, but it's very responsible for total reflection to take place. Right. Now, let's point one important thing about this. One important fact about reflection by a mirror. Reflection by a mirror is not due to total internal reflection. Now check why. Remember, for TIR, total internal reflection, to take place, for total internal reflection to take place, then mu1 is greater than mu2. Remember that. But in a mirror, reflection takes place when mu1 is less than mu2. So it's not TIR. It's not TIR. It's another process. But we are not going to discuss it here. It's beyond the scope of our topic. So we won't discuss how that happens. It's another different process. But it's important for you to understand that it's not really total internal reflection, because total internal reflection takes place when we move from higher optical density to a medium of lower optical density, and it involves two transparent media. Now in this case we have a transparent media and a solid material at the back of the mirror. So we move from lower to a higher optical density, and the process is different in this case because the two media also are not both transparent materials. So it's not total internal reflection in the sense we have just studied, but still it's a complete total reflection taking place. Right. So let's look at what is specular reflection. Let's look at what is specular reflection. Now, at specular reflection, we can demonstrate it by having an interface, right? And here we have our mirror. Now check, a mirror always has a very smooth surface. It is a very smooth surface at the reflective side. Right. How does this help reflection? Now, when light approaches the mirror, let's suppose we take parallel rays which are incident on the mirror as they come in. These rays are reflected in the same manner in which they came in. This is an incident beam. Let's call it an incident beam. And this is the reflected beam. Now check. When we talk of a beam, it's made up of several rays. Actually, there are a lot of rays in a beam, but here we are just representing a few rays in the beam. So these rays, they come in and strikes the interface. This is the point of incidence. Now, if you were to draw a normal, you could have normals here, another normal there, another normal there. Now, the rays are reflected in that direction, but check, they are parallel. And when they are reflected, they are also parallel. In other words, the incident rays are parallel when they are incident on interface. And they are reflected still parallel at the interface. In other words, the reflection takes place maintaining the same angle of incidence for each ray. Now, so we say then that specular reflection retains the geometry of the beam of light. It retains the geometry of the beam of the light. Look at this. It's retained. This geometry, they are parallel, equally spaced, and the same happens to the reflected rays. So each time the incident rays which are parallel to each other reflect off the surface, they do so at the same angle equal to the angle of incidence. Therefore, they maintain their parallel geometry as they reflect off the surface. Right. Now, the reflection, check, the reflection must take place always in such a way that it must fulfill the law of reflection. Reflection must comply with the law of reflection. In other words, it must satisfy the law of reflection. Theta 1 always equals to theta 1 prime. Right. In other words, here we are. This is the interface. The incident ray reflects at point of incidence here. This is point, this we call it point of incidence. Point of incidence. It reflects off at point of incidence such that the angle of incidence is equal to the angle of reflection. Right, and this is our normal. This has to be complied with. Right? In other words, we are talking of the law of reflection must be satisfied. And remember also, according to Snell-Descartes laws, the incident ray, the normal, and the reflected ray must all lie in the same plane. In other words, and the incident ray, normal, and reflected ray must all lie in the same plane. These two conditions must be satisfied when a reflection is taking place, especially when we are talking of specular reflection. Diagrammatically, I can say, for example, let's say this could be our plane of incidence. Now, we can draw here like this, right, and say like that. Right, this is the plane of incidence. We call this plane of incidence. Now, here, this is where, for example, we can put our normal. And the incident ray comes up to point of incidence. And it's reflected. Right. This is the angle of incidence. This is the angle of reflection. This normal, this is our normal. This normal, this incident ray, this reflected ray, they are all in this plane. They are all in this plane, which we call plane of incidence. Plane of incidence. They are all in this plane. This plane, we call it reflecting surface. This is the reflecting surface. Right. So, this is what happens under specular reflection. Now, let's talk about diffuse reflection. diffuse reflection. Now, under diffuse reflection, it occurs on rough surfaces, does not retain the geometry of the beam. Of light, does not retain the geometry of the beam of light, only the energy, of course. Right. What do we mean? Diagrammatically, we can say here is the interface or the surface. Now, this is an ordinary object. This is not a mirror. This is an ordinary object. Now, let's suppose you have your parallel rays. They are coming, the rays. They come. They are parallel. And they strike the object. Now, what happens is now, the ray, let's say for ray 1, it goes in this direction. Then you find that for this ray, it goes in this direction. And you find that for this ray, it could be going in this direction. Now, each of the reflected rays, this reflected ray, this reflected ray, this reflected ray, has its own direction. Each of the reflected rays has its own direction. Whereas the incident beam has parallel rays. But these ones are not parallel. Reflected rays are not parallel at all. They are not parallel at all, but go in different directions. Right. So we can then say when light strikes a rough or granular surface, it bounces off in all directions. Now, the reason why does it do so? Why does it do so? Because they are microscopic irregularities on the surface. Right, meaning to say the surface really will be probably like this, like that, like that, like that, like that, like that. But this cannot be seen. These are irregularities of the surface. But they are very microscopic. These are rugged structures here on the surface. These are rugged structures on the surface. They are very small. You can't see them by your naked eye. They are microscopic. And these rugged ones are the ones really that cause light to reflect in different directions. So this is called diffuse reflection. So we are saying when light reflects in different directions and does not maintain the geometry of the incident beam, then we have diffuse reflection. We have diffuse reflection. The surface is made up of many small randomly oriented. This is the surface. Is made up of many small randomly oriented plane surfaces, such that each ray reflects in a different direction from its neighbor, even though each ray does obey the law of reflection. That is very important. Don't think the law of reflection is violated. It doesn't apply here. It applies. The law of reflection is still observed in diffuse reflection. Right. So this is what we can say about the difference between specular and diffuse reflection. This is what we can say about this kind of reflection. Okay. Now, this is the end of part 1 in this video. We are going to look in the next video about image formation by mirrors. Image formation by mirrors in the next video. Right. Good luck.